Imagine a chemistry lab in the early 1600s. There are no electric hot plates, no digital temperature sensors, and no microscopes powerful enough to see a single molecule. Yet, to create medicinal compounds, vibrant textile dyes, and the specialized materials needed for early scientific experiments, researchers required chemicals that were consistently pure. They were working in a world of contamination, armed with little more than charcoal fires and glass pots. To extract pristine materials from dirt and ash, they needed a physical mechanism that didn't require modern equipment. They relied on crystallization. By dissolving an impure solid into a liquid and letting it cool, they watched as a chaotic mixture reorganize itself into sharp, solid geometric shapes. In doing so, these early scientists utilized the physical behavior of molecules centuries before they had the tools to actually see them. The process begins by increasing the solubility of a substance. Chemists heated water over a charcoal fire to force solid material to break down and dissolve. They added their impure material to the boiling pot little by little. Because hot water can hold much more dissolved material than cold water, they were able to pull the chemical into a liquid state. Not everything dissolved. Solid debris like dirt, sand, and plant fibers remained in the pot. To remove debris, the hot liquid was strained through linen or cotton cloth into a container. At this stage, the resulting liquid looks perfectly clear, but that clarity is an illusion. On a microscopic level, dissolved contaminants are still entirely present. They are mixed in so thoroughly with the desired chemical that no cloth filter can ever reach them. Mechanical filtering only removes what we can see. To target the invisible impurities, chemists had to use the way molecules interact with one another. The next step is to remove the heat and allow the solution to cool at an extremely slow pace. As the temperature drops, the water's capacity to hold the dissolved molecules shrinks. This forces the chemical to fall out of the liquid and return to a solid state. As they slow down, the molecules of the desired chemical begin to find each other, locking together in a consistent, repeating pattern. They don't form random clumps. Instead, they build a three-dimensional lattice, a rigid, geometric grid. This grid is the key to purity. Because the lattice is so specific, impurities are the wrong shape to fit in. As the crystal grows, these contaminants are physically rejected and pushed away. The rejected contaminants remain trapped in the leftover liquid, known as the mother liquor, while the solid crystal continues to grow cleaner. Finally, the chemist carefully pours away the contaminated mother liquor, leaving only the pure solid crystals at the bottom of the vessel. The effectiveness of crystallization comes from building a structure so specific that impurities are simply locked out by the physical constraints of the grid. A single cycle of this process is highly effective, but microscopic traces of the mother liquor can still coat the surface of the new crystals. To reach even higher levels of purity, chemists used recrystallization. They took the clean crystals, dissolved them in a fresh pot of hot water, and started the cooling process all over again. This chart shows how the process works over multiple cycles. If one pass removes 90% of the contaminants, a second pass removes 90% of what's left, driving the impurity level towards zero. By repeating this simple loop, 17th-century chemists created a reliable method of purification that scaled in cleanliness with every successive repetition. Today, our laboratory equipment is powered by electricity and managed by digital software, and we have a complete understanding of how these molecules interact. As industrial demand grew for dyes and salts, manufacturers took this manual technique and scaled it up into massive vats to produce chemicals for the global market. Modern pharmaceutical facilities are now cleanroom environments, filled with pressurized stainless steel reactors that cost millions of dollars to maintain. But inside those high-tech steel vats, the core mechanism remains exactly the same as it was 400 years ago: a hot solution, a slow cooling, and the growth of crystals. This process continues to provide the life-saving purity needed for modern medicines and the consistency required for the sugar in our food. Technology has replaced charcoal fires with automated sensors, but the underlying physical process, the way cooling molecules pack themselves into orderly solids, remains the standard for chemical purity today.